Hello, this is Professor Matt Katroulis of Rio Hondo College, and I'd like to welcome you to the first video lecture for our Chemistry 110 course entitled Chemistry for Allied Health Majors. This is Chapter 1 on the topic of matter and measurements, and this first video will focus mostly on this first term, matter. But before we get too much into that, we might ask ourselves, well, what is chemistry? And the definition of it is that we say chemistry is the study of the properties and, very importantly, the changes of matter. The problem, of course, with that definition is we need to know what matter is to really understand that definition a bit better. And even after what I'm about to tell you, that definition is still going to be a bit vague until we've proceeded a little bit further in the course. So we'll define matter as anything which has mass and something that takes up space, which is to say it has volume. And we'll have more to say about mass as we go on. Right now, we might just kind of point to a vague idea of, well, it's something you can put on a balance or a scale and it will show having some weight. Not very exact of a description, but it's a good way to sort of start for the moment. So let's take a look at some examples of what we might consider matter. So sand, which would be a solid form of matter. Water, which is a liquid. And air, which is a mixture of various gases, a mixture of what we're going to call elements and compounds as we get a little bit further on. So a worthwhile question is, how do we actually learn chemistry? Well, we say that chemistry is an empirical science, and by that what we mean is that it is based on the results of experiments. And experimentation in chemistry has been going on for many, many years, long before we even called it chemistry. And so in the lecture I talk about these theories and laws that we've developed, and then in the lab, to an extent, we verify these principles, and we also make a lot of observations that are critical about many different substances. So we're going to be really focusing in this class on what I consider to be the most fundamental concepts, the most essential things to understand about chemistry. And to really do that well, you need to develop a good method in your mind for visualizing chemistry. And through the various artwork that you're going to see here, the artwork in your textbook, that should help to guide you to be able to see matter at the smallest possible level, what we call the submicroscopic level. That means even a microscope, a normal microscope that you would use, say, in biology, can't get down to that level. So the level of what we'll call the atoms and the molecules, which we'll talk about soon. And if we're good at looking at matter at that level, we become able to reason as to understanding why matter behaves the way it does, why there's certain attractions between certain particles, and why other particles, for example, don't mix very well. And once we understand the submicroscopic level, it leads us to a better understanding as to why things behave the way they do on a macroscopic scale, which is things that you can see in your ordinary daily lives. So it's an essential skill for a good scientist, and you also really will benefit a lot from a very good imagination. So let's just take a very simple process, like ice being heated up just by the atmosphere and turning into liquid water. A non-chemist just sees melting ice. But to a chemist, what we see is much different. What we see in our mind is that this is not just a solid, but it's a solid with a very organized structure. And in fact, we can see little hexagons here within the structure. And we see that that order is significantly reduced when it goes from being a solid to a liquid through the process of heat. And we see that the particles are still close together. That's important, but they are no longer have the same degree of organization as they did in a solid. And we'll learn why this is going to be the case as we move throughout the course. So let's talk about the very most fundamental concept of matter, and we're just going to hint at it right now, and that is the atom. We'll spend much more time on the atom in Chapter 2. But it's the most fundamental unit of matter, the most essential that we'll talk about. And all the matter that we encounter in our daily lives as a vast number of atoms. Not thousands, not millions, not even billions, but usually billions upon billions in anything that you can see. Even a grain of sand will have billions upon billions of atoms within it. Now, there are many different types of these atoms. They aren't unique, but some of them are hydrogen, oxygen, gold, sodium, and many, many others. Helium, neon, nitrogen, etc. It goes on and on. And we'll look very closely at what makes up these atoms starting in Chapter 2. Now, atoms can come together and form what we call molecules. And molecules are held together by bonds. There has to be something that would keep the atoms together. And in molecules, we're going to call those covalent bonds. Again, this is a topic we get into a little bit later. And we'll go a little bit further with this and say that we have many important diatomic molecules, which are molecules that contain two atoms. And so we'll see some pictures of those as we kind of progress through here. So let's take a look at how we might represent molecules in a picture form. So I'm going to use here a white circle to represent a hydrogen atom and a green circle for a chlorine atom. You'll notice that I've shaded it to try to indicate that there's some three-dimensional qualities to this. So it wouldn't just be a circle, but a sphere. The same for this one here as well. So these are atoms. And then when I join atoms together, they form molecules. And specifically, this is called a diatomic molecule because it has two atoms, two hydrogen atoms specifically. And I can do the same thing here with chlorine. This is a diatomic molecule because I'm showing them joined together. And then I could make a diatomic molecule of hydrogen and chlorine. Now, matter is going to come in one of three common physical states. There are technically four, but we're only going to focus on three. And they are gases, liquids, and solids. In trying to understand and differentiate between these three, what we're going to do is ask ourselves two questions about each of these. So the first question is, does this substance have a definite shape, or does it take the shape of its container? So imagine if you put something in a box, does it take the shape of that box, or does it just maintain its shape? And then also, does it have a definite volume? And by definite volume, what we mean is, can it expand on its own and contract on its own into a smaller space, or does the amount of space it takes up seem pretty much predefined? Well, solids have a definite shape, so it doesn't really matter what the container is that you place them in. They will keep their shape. Now you might say, well, what about sand? Sure, if you put sand in a bottle, it will fill into the shape of the container. But the various individual grains of sand don't change their shape when you do that. They stay the same. And solids have a definite volume, meaning that they don't expand or contract regardless of the container you put them in. So a sub-microscopic definition of looking at solids would be that the particles that are inside the solid are very close together. They don't move by much, but they do vibrate in place. So there's always some motion, but relative to each other, the particles stay in the same place. And they tend to form organized patterns, although that's not always true. For example, in rubber, the atoms can move about when the rubber is stretched. So let's say that, for example, this is going to represent a gold atom. When we look at solid gold, we might expect to see a structure somewhat like this. You'll notice that it is nice and organized. There are hexagons here, and While it might seem that I'm obsessed with hexagons, that's because that is one of the fundamental structures of matter at the subatomic level. So there's a nice organized structure, and you will notice that the atoms are very close together. Here I have a sodium ion and a chloride ion. We'll learn more about ions shortly, but for right now let's just say that this is a slightly modified type of an atom, and we'll get into how in the next chapter. So this is what sodium chloride might look like in 2 dimensions. You'll notice that the particles are close together. They're not exactly touching, but they're in a very organized pattern, and that's typical for what we would call a crystalline solid. So more on ions and ionic solids later on in the class. Let's move to the next state of matter, which would be liquids. Now the shape of liquids is indefinite, so their shape depends on the shape of their container. If you put liquids into a plastic water bottle and the water bottle has ridges, then the liquid will take the shape of those ridges. But liquids do have a definite volume, so when you pour a liquid into a container, they don't suddenly expand to fill up the whole container. When we look at the particles of a liquid on a submicroscopic level, we see that the particles are fairly close together, and sometimes almost to the same extent as solids, but usually there's a little bit more distance to them, although there are exceptions. And the particles are able to move freely throughout the liquid, although they essentially have to roll over one another to get from one section of the liquid to the other. But they are not organized in a pattern like we would have seen for solids. So for a moment, let's examine that this sphere here stands for a mercury atom. Well, mercury is one of 2 elements which is found at room temperature as a liquid. So how would we represent it as a liquid? Well, we see the particles are close together, but you don't really see any pattern here, do you? They're just kind of amorphously organized, and that would be typical for a liquid. Gases have an indefinite shape, like liquids, which means that they take the shape of the container that they're in. Unlike both solids and liquids, gases have an indefinite volume, which means that they can expand to fill up their container, or if they're put in a special type of container, they can be compressed into even smaller volumes. So the particles that make up a gas, when viewed on a submicroscopic level, are going to spend their time usually very far apart from one another. And they are able to move throughout the container in a totally random fashion. So if each of these spheres stands for helium, what we see is that compared to the other pictures we've seen, the atoms are much farther apart from one another. And these lines here are meant to indicate that these are moving throughout the container. So for example, this helium atom is moving right towards the side of the container right there, and this one is moving this way, and this one is moving this way, and they're not all moving at the same speed. So they are moving randomly through the container and essentially are oblivious to the existence of one another. Our next area of interest here is going to be in classifying matter. So we can classify matter in 2 different categories. First of all, as a pure substance, or also as a mixture. And when we look at pure substances, we're going to divide those even further into 2 main categories, the elements and the compounds. For a moment, let's focus on the pure substances. So an element is going to be something which contains only one type of atom. So for example, gold is an element, and if we have a sample of pure gold, 100% gold, then the only thing in it is going to be gold atoms. Helium also is an element, so it contains only helium atoms. You'll notice that so far up to this point we have represented atoms as being spheres, and different colors have represented different elements. At the moment at which I am speaking, there are 118 known elements. They cannot be broken down into simpler substances by any chemical reaction. They are the most fundamental unit of matter. Every element has its own unique name, and it also has a symbol, and we'll be using those symbols a lot in this class. And a symbol has one or two letters, and if there's only one letter, that one letter is always a capital letter. And if there are two letters, then the first letter is always a capital, and the second letter is always written in lowercase. And what we will spend a lot of time on coming up soon is the periodic table of the elements and understanding how it's structured and why it's structured that way. So right now it might just look like a list of all the different elements with their symbols. And for right now, if that's how you see it, that's fine. So here are some different symbols. So H for hydrogen, O for oxygen, C for carbon, N for nitrogen, the four most basic elements of life. And those make a lot of sense. But what about these four here? Sodium is Na, and there's no N or A anywhere in the name. Copper, with a U, has no U. Potassium has a K, and obviously there's no K anywhere in the word potassium. And Cl for chlorine. And so you'll find that some of these symbols are unusual. They're not done that way randomly. It's because these elements have symbols which are based on their Latin names. So if we wanted to look at some samples of some elements, if I said that this stands for a gold atom, you'll notice that a sample of gold only contains one type of atom. They're all the same type of atom. This is showing that we have a solid because we have a nice organized structure of the atoms. Here is mercury, which is a liquid element at room temperature, and you'll notice it's all the same color here to indicate that the atoms are all the same. And here is that same picture we saw earlier of helium, so it's all the same type of atom bounding through space randomly. Now, what we can find is that many of the elements come together in whole number ratios, and when they do that, they form compounds. And a chemical formula is going to list the ratio of those elements in the compound. So, for example, in water, the chemical formula is H2O. And in the case of water, that tells us that there are exactly 2 hydrogen atoms for every 1 oxygen atom in a unit of water. And we call that unit a molecule, a term we've already seen. Here are some other examples. Sodium chloride, which is essentially table salt. Silicon dioxide, C6H12O6, which is the formula of glucose. Now, the formula, or ratio, is always the same for a particular chemical compound. That never changes. However, it is possible for different compounds to have the same formula. I very carefully said that this was the formula of glucose, but it is also the formula of other compounds as well. For example, fructose, galactose. Those are just 2 of the other compounds out there that have that same formula. So compounds are said then to have definite composition. Their formulas do not change. So here what I'm trying to do is represent 2 different compounds. So here I have water, where my red dots here stand for oxygen and my white dots stand for hydrogen atoms. They are forming molecules because the atoms are joined together. You'll notice that they kind of look like Mickey Mouse ears here, and there's a reason for that. We'll talk more about the shapes of the molecules as we get further in the class. And then this is carbon dioxide, which has a dark colored sphere to stand for carbon, and then 2 oxygen atoms on opposite sides of that carbon. Now, moving away from the pure substances, we're going to look at the mixtures. So the composition of a mixture is not fixed, in particular its ratio. So let's say we took salt water. Salt water is a mix of water, which is a compound, with sodium chloride, which is another compound. Is salt water always found in exactly the same proportion? And the answer to that is no. Well, what if someone said, okay, how about 5% salt water? Well, that does seem to define a ratio, but no matter how close we try, there's really no way to get to the same atom-to-atom ratio. We aren't going to be able to get down to that level of measurement. It's simply impossible, at least as of this point in time. Now, mixtures can also be classified into two different types. There are homogeneous mixtures, and with a homogeneous mixture, all parts are in the same state, gas, liquid, or solid, and all the parts have to be completely mixed together. And so we're going to say that a mixture is homogeneous if it visually looks the same all throughout. So if you look at the top, you look at the bottom, you look left, right, it looks completely the same all the way through. We would consider that a homogeneous mixture. And heterogeneous mixtures are going to be just what's left over. Mixtures which are not homogeneous, meaning that their parts might be in different states, so a gas mixed with a liquid or a solid mixed with a liquid, or their parts might not be completely mixed together. And we're going to visit mixtures a little bit more in detail in Chapter 7. So let's take a look here at a simple mixture. This is salt mixed with water. Does the top look any different from the bottom? Not really. The glass does look different there, but that's the glass. So this is a homogeneous mixture. It's consistent throughout. Versus mud. Mud is going to, you'll notice, have a solid here and a liquid here. It's not the same throughout, and in fact you'll notice even at the surface that it's clearer than it is at the bottom. So this is a heterogeneous mixture. It is possible to separate mixtures by what we're going to call physical methods, meaning we don't need to use chemicals to accomplish this. So a very simple example would be coffee. If you make coffee by adding hot water to coffee beans, the heterogeneous mixture of water with the coffee beans is separated by filter paper. So the coffee grounds stay behind on the paper while the coffee, which is a water mixture, passes through. If we have salt water, we can separate the salt from the water by boiling the water off, something that we'll do in the lab later on in the semester. And the salt simply remains in the container. Compounds, on the other hand, cannot be separated by any physical method. You have to use some kind of chemical means or electrical means in order to separate these. So some kind of a chemical process has to occur. So let's take a look at these pictures here. These are two different elements. This is iron, and this yellow powder here is sulfur. We'll notice here are two different, what we would call physical properties of iron and sulfur. The iron is attracted to a magnet, the sulfur is not. Let's say I pour the sulfur into the test tube with the iron and I give it a good shake. Shaking them does mix them up, but it doesn't make a new compound. They don't react with each other. So you'll see that I can still separate the iron from the sulfur using the magnet. Let's say we were to go ahead and heat this mixture up very strongly. If we heated it up extremely strongly over a flame, this would cause a chemical reaction, and this forms the compound iron sulfide. So the atoms are now bonded together, and they are in a very strict whole number ratio. Now here I'm using a magnet. Is the magnet able to separate the iron from the sulfur? And you see, no. It is not possible to separate a compound using a physical method like a magnet. So I would like you to classify each of these as an element, a compound, or a mixture. Helium, mud, carbon dioxide, oxygen, Coca-Cola, and aspirin, also called acetylsalicylic acid. Take a moment to write these down and classify them. And when you're ready, I'll go ahead and go over these. So just pause the video for the time being. Okay, I'm assuming that you have just unpaused the video, and I want you to classify each of these. So helium, recall I mentioned, was an element. Mud, I gave an example, had water in it and it had other things. Water is a compound, and those other things were also compounds. So mud is a form of mixture. Carbon dioxide, I showed you when we were talking about compounds. It has a formula of 1 carbon to 2 oxygens, and that never changes. Oxygen is an element. We can find it on the periodic table. Coca-Cola, well, Coca-Cola contains water. It contains sugar, so those are 2 different compounds right there. So if I've got 2 or more compounds, it must be a mixture. And aspirin, you'll notice I'm giving you here a formula, so that's telling you that aspirin is a compound. Now, an aspirin pill would technically be a mixture because it contains not only aspirin, but other chemicals called binders, which are designed to hold it together. I'm going to go ahead and end this video here for this part of Chapter 1. And when you're ready, you'll want to continue on to the part of Chapter 1 which focuses on measurements. Thank you.